SwayamPrabha. Digital India. Educated India.
Okay, so we'll start discussing about sandwich structures, which is one of a very commonly used method to come up with lightweight structures. Lightweight structures are of great demand in the automotive and aerospace industry, as well as in many other industries such as like the sporting goods or even these wind turbine blade constructions. So the reason why we are discussing about these sandwich structures is because this is a one very good example of laminates. We will see in next slide how this is related to the laminates and see the mechanics of the laminate we have studied, how it can be applied even while discussing about or designing these sandwich structures. So here is the image shows a sandwich structure which has three constituents. First is the face material. So we have one face material at the top and another face material at the bottom. So it is a pair and usually these are symmetric, meaning the top layer and the bottom layer are made up of the same material or the same thickness and the same geometry. Second is the core material which is at the center. So usually there are many different core materials people use. What you are seeing here is a honeycomb. Hexagonal honeycomb could be made up of materials like aluminum. And lastly, to join this face and the core, we need a third layer in between, which is the adhesive. This adhesive helps to bond this face sheet to the core material. So these three constitute, and then we get what we call it as the sandwich panel. So as the name says, it is just a sandwiching few layers together. And here what is it sandwiching? The face sheets and the core materials. How are they bonded? They are bonded using this adhesive layer. But now let's see what is the speciality of this face sheet and the core materials. Face sheets we are saying are usually thin. Compared to the thickness of the core, these are thin. But then we choose materials which are very stiff and strong, like high alloy aluminum or titanium, or even like the fiber reinforced composites. So these are all the face sheets we can use, which can give you high strength and stiffness. But for the core material, usually we choose that the thickness is very high, and we choose a material which is lightweight. So now let's see what is the advantage of the sandwich panel and how does it uh, achieve the lightweight structure. So the basic idea is, here we are trying to separate the skins. Skin is the other name for the face sheet. So if we move these face sheets apart and then fill this intermediate space with a lightweight material, essentially we increase the moment of inertia of this composite or the sandwich panel. How does it increase the moment of inertia? For this we need to think about the analogy of an I-beam. So in the solid mechanics or the mechanics of material course in the undergraduate, most of us have read about these I-beams and why they are mostly used. So the basic idea about this is, when we move the mass away from the midplane, so the greater is the distance from the midplane for the same mass, the more is the moment of inertia. And I-beam achieves this because the majority of the mass is focused at the ends, and these are connected using a thin beam. So we use the same concept also in these sandwich panels. So we are focusing on the thick and stiff face sheets. So even in, let's say, if I have to show this sandwich panel as a cross section, this is how it is shown. So you have a face sheet at the top and the face sheet at the bottom, and intermediate is the core. So this is the mid surface we are showing. So here we have seen that the face sheet which has the mass and which has a higher stiffness is away from the midplane, and this is separated using the core. So this explains why the bending stiffness of the sandwich panels are much higher compared to the panels prepared from the same mass materials but which are made up of like compact without the core. And to illustrate this example, let me show you with an example. So here we are looking at three different constructions. Let me draw and show. So the first case is we are saying it is a plate of thickness T. So let's say we cut it into two halves, so but the total thickness is T. We can think of it as the top face and the bottom face. Now for the same plate, we can let's look at double the thickness. The only difference we are doing here is we are moving this top plate and bottom plate, and in between we fill it with a core. But we are saying the total thickness is 2T. And in the third case, we are now saying from double the thickness, we go to 4 times the thickness. So the total thickness is 40. So let's assume the mechanical properties of usually commonly use the face sheet and the core, and this is a table to give us an indicative values of how the relative weight changes. Correspondingly, what is the changes in the relative bending stiffness and the bending strength. So let's say we normalize it with the first case where we have thickness T. But now once we move to the second case with twice the thickness, we see the relative weight, there is a 3% increase. It went to 1.03. So just with a 3% increase, let's see what happens to the bending stiffness and the bending strength. We see there is a 7 times increase in the bending stiffness and 3.5 times increase in the bending strength just with a 3% increase. And now in the last case where we are looking at 4, 4 times the thickness, the mass increased by 6%. Where is this 6% mass coming from? Because this is the extra mass we placed by placing the core. But as you can see, the bending stiffness increased tremendously. It increased by 37 times the initial reference values. And the bending strength increased to 9.2 times the initial bending strength. So the increases are, if I have to talk in percentages, so we have gone to 3700 and 920%. With just 6% increase in the mass, we are able to achieve a significant increase in the bending stiffness and the strength. This should give a clear idea about why sandwich panels are very commonly used in lightweight structuring. Because with this example we have shown there is a significant increase in the stiffness and the strength with a very little additional mass. Now let's focus on the constituent materials we use for the core as well as the face. So let's start with the core constructions. We start with the corrugated core. So this is the corrugated core we are talking about. As we see, there is a pattern which is repeating itself. Usually these are made with metals and most often with aluminum. So essentially we take a flat sheet and then bend it into these corrugated shapes. The reason why we use it as a core is because since we are bending, there is lot of empty space and that reduces the mass. Okay. So the next is foam core. So meaning like we fill it up with foam, and usually these foam materials are made up of polymers like polystyrene, PVC, and other polyurethane, PU. These are the commonly used foams. The other advantage, in addition to the mechanical properties which we have been discussing, those foams, these polymer foams also increase the thermal insulation properties. So in addition to the mechanical advantages, it also give you the thermal insulation benefits. So foam cores are commonly used in the construction industries. And lastly, these honeycomb cores, this is same core which I have shown in the previous slide. Essentially, we call it as honeycomb because it replicates the honey beehives, which are again in the hexagonal shapes, and most often these are again made with aluminum sheets. So this is a very inexpensive manufacturing process, but the reason why majority of the industries use honeycomb core is because the benefits like the stiffness increase or the strength increase is much better compared to other alternatives in the core constructions. Now moving to the face materials, we have two options. Either we can go with metallics, like we can use high strength alloys like aluminum alloys, or they can also be replaced with titanium or these days with magnesium face sheets. And the second commonly used material is our composite laminates itself. It can either be a single layer of CFRP, GFRP, or any other fiber reinforced polymer, or a complete laminate itself. So it could again be the face sheet itself could be again like 10 to 20 layers of different lamina. So usually when we work with space structures, there we use these laminates as the face sheet, and these laminates can be made up of CFRP because they are comparatively much stiffer and stronger compared to the other laminates. So lastly, we'll focus on the failure modes, but for this we'll focus only on the honeycomb structures and see what are the different failure modes these composites have. First, we'll focus on skin failure modes and later we'll focus on the core. First is yielding. So in this we have seen there is a compressive load, and then since the face sheet, let's say, is made up of a metal, then we assume the first kind of failure will be it going into plastic deformation. So when does it go to plastic deformation? When it starts yielding. So this is what we are calling it as face yielding. But let's say what are the other failure modes we expect because of these kind of compressive loads? We expect buckling. But in buckling, there are two different ways which we'll show here. Currently, what we are focusing is on the intracell, meaning this buckling happens in each cell. In each cell, there is an unbonded area. So let's say this is the one of the cell and here is the face sheet. So this face sheet buckles in one of the cells like what is shown here. So in contrast to intracell dimpling, we have the face wrinkling. Here, the buckling is concentrated not just on a single cell like intracell dimpling, but it is focused on a group of cells. So that's the major difference between an intracell and the face wrinkling. Now moving into core failures. The first or the majority of the failures are because of core shear. Because let's say there is an offset in the loads because of the high thickness of the core, now it is easy for the core to shear and fail. But there is another failure mode which is again indentation, where we see it is very close to face wrinkling what we have seen for the skin failures. But in here again we see a group of cells will take the indentation. So now let's summarize what we have discussed here. This is a brief video to show you what is the advantage of using sandwich panels. So we said it is made up of the face sheet and the core joined using an adhesive, and it improves properties such as the stiffness and strength. We are looking at the specific strength and the specific stiffness. Later we also discussed about the different sandwich materials we use. So starting with the face sheet, we said face sheet can be metallic or composite or laminate. Or laminate. But for a core, we said there are different constructions starting with the corrugated, mostly made up of again aluminum sheets. The second is we can have polymer foams, but in addition to polymer foams, these days there are also people use metallic foams because these are good in energy absorption. And lastly, we also discussed about the honeycomb cores, which are very commonly used in the automotive and aerospace industry because of their extremely high stiffness and strength. And lastly, we also showed you few commonly occurring failure modes, both for the face sheet and the core. So with this, we will conclude this video. Thank you.